Thank you. I'm really excited to present this work with my collaborators, Ramon, Amal, and William, whose faces you can see up here, but they're not life-size. Okay, so before I start talking about the technical details, I'd like to give a little bit of a larger picture here. What we're interested in exploring is how can we compile high assurance software and ensure its correctness when linking with an unverified world. So one approach to this that we're interested in exploring is to preserve these invariants that we impose on this high assurance software and keep these invariants around until link time so that we can check that these invariants aren't violated when we link with external code. This is all very large and vague, so of course I'm going to be talking about the smaller picture here. And the smaller picture here is about preserving these invariants through one necessary pass of a functional language compiler. So to start talking about the smaller picture, I'm going to decompose the title of my talk to give a little bit of a background. And here the background, I'm going to start with what it means for a compiler to preserve dependent types. So the definition of dependent types is quite simple. It's just types that can refer to or depend on program terms. But this simple statement has quite a large implication. In particular, now we can encode highly specific invariants in the types. Then when we type check our program, we're essentially proving that our program meets these invariants. After we spend so much time in our dependently typed language proving these invariants and encoding them, we'd like that these aren't violated by the compiler at link time. So this is where type preserving compilation can help. So the idea here is we take our dependently typed program, compile it with a type preserving compiler to get some output with types. And then when we link with some external code, we type check to ensure that the invariants of the original program aren't violated by this external code. And here the external code could be compiled by a different compiler, handwritten, etc. And in principle, when we use type languages, this is how we want to use them, right? We use libraries all the time. We don't know the implementation. We just want to check the types. So why not do this after compilation? Okay, so continuing with decomposing the title of my talk, I'm going to talk about a specific translation, the ANF translation, as a part of compilation. So ANF stands for a normal form, and it's simply a syntactic form for making control flow explicit. And we essentially this is done by just unnesting our functional expressions and making them execute more statement by statement imperatively, like we just saw. And so as an example, we have a functional expression here in non-ANF form, just a second projection, some extra computation going on here. And then in ANF, it would look something like this, where we'd first compute 1 plus 1, then construct the pair, then take the second projection of it. And yes, it is a normal form. If you're interested in learning more, there's a blog post by a crazy person, by William. So I definitely recommend checking that out. Okay, so just to wrap up my title, let's talk about what extensional equality means in dependent types. So equality in dependent type theory is important in general, now that we have terms in our types. We have the canonical dependent vector type that is used in every dependent type theory talk. And we have a whole bunch of different terms for the length of this vector, right? But our type system can determine that these are all the same type by essentially just partially evaluating all these terms. So in the first case, 1 plus 1 is 2. And in the second case, n is defined to be 2. So we can conclude that these are the same type. But suppose we have a different example where we don't actually know that n is 2, but somehow we've gotten a proof that n is 2. So our partial evaluation can't actually use this proof of n being 2, so we need some other way of telling the type system to use this proof. The usual way is by constructing a new term. Here I call it subst, and it takes 2 arguments, the proof and the term of which type you'd kind of like to subst in or convert. And this term itself has the type vecnat2, right? So anytime you want to use my least favorite vec as something of vecnat2, you actually have to pass in the subst term. So again, it's not happening in the type equality judgment, but in the type system itself. So suppose we'd like to actually just use these proofs directly in our type equality judgment. This is what we know as extensional equality. So in this case, we would directly use the proof n is 2 to reflect into the type equality judgment that n is 2, and then we can conclude that these have the same type. And this is very different from definitions before. In definitions, we were using partial evaluation. Here we're taking the actual proof that we have and reflecting it directly to the type equality judgment. So just to summarize, the formal rule looks something like this, that E1 is considered equivalent to E2 by the type system if we have some proof P showing that E1 is equal to E2. Okay, so I think that summarizes my background. We have an ANF translation that preserves dependent types, provided that the target language you translate to has extensional equality. But before I talk about the technical details of our translation, I'm going to start with everyone's favorite example, which is if expressions, which have come up a lot during the session. And so here in a dependent if expression, we can actually reflect the dynamic control flow information into the type system. We do this using a dependent type, where the type B can refer to the condition E through the variable X. And as you might expect, now X is replaced with true in the first case, because that's what the condition is, and false in the second case. So I want to talk about a simple refactor we can do with dependent if expressions. Here we have a function that's expecting one of these dependent types, so we can freely apply this function onto the dependent if expression. But suppose we'd like to refactor this to unnest these expressions a little bit. Maybe make this if expression behave more like an if statement. So we do this by pushing the function application to the branches. So dynamically, we know these programs should behave the same. But when we get around to type checking, we find that it fails because E1 has this type where X is replaced with true directly, not the condition E. So this is extremely frustrating. And it turns out this relates to ANF because this is a part of ANF, right? So not only are we kind of sequentializing our computations here and making these assignment statements, but we also want to kind of expose these if expressions and make them behave a little bit more like if statements. So in order to preserve dependent types through a translation like ANF, we need some way for the type system to be insensitive to these kinds of syntactic changes. So how do we go about doing that? Well, in particular, when we're type checking each branch, we need to know that the condition has changed. We need to be aware that E is now true in the first case and false in the second case. So this leads me to a key observation in our work, which is dependent types are hard to preserve through compilation. And so our intermediate type systems need some way to express these equivalences that we rely on in compilation. In our case, these semantic equivalences are these syntactic changes we want to make control flow a little bit more explicit. So the way that we do this in this work is in our target type system. When we check let expressions, we want to record the definition so that the type equality judgment can use this definition during partial evaluation. This is very standard in dependent type theories. But what's a little bit less standard is now when we check each branch of the dependent if expression, we need to record the fact that the condition has changed. And we do this by recording a proof in the context. Okay, so now that we have a little bit of background, why it's hard to preserve dependent types through compilation, let's talk about how we actually did it. So I mentioned this refactor earlier is a part of ANF, but really it's a more specific case of something we want to do more generally. So in particular, we have some context surrounding our if expressions, and we want to kind of pull the if expressions to the top level by pushing the context into the branches. So this leads us to define the ANF translation over source expressions and target contexts. So here, let's look at the case for dependent if expressions. So as we're translating dependent if expressions, we correctly translate each branch with respect to K as expected, but we find that we're kind of missing what we need for the translation of the condition E. We need to unnest it a little bit further. In particular, we also need to know that it's going to be embedded in this if expression context. So we need some way of encoding this. The way that we do this is by encoding the context into a program with a hole. This hole happens to be the right-hand side of a let binding. This is to ensure that we always have some concrete value of the variable y, so that we can build up target terms in ANF. And as a further example of this translation, so for value cases, we know we can just plug those in directly into the context because we're done unnesting expressions. And then at the top level, we start off with the empty context. Okay, so let's think about how would we prove type preservation for translation defined with context. Well, our top level statement doesn't have access to these contexts, right? I have the base case here just to illustrate we're still working with these contexts. So really we need some sort of invariance about this target context. So in order to prove type preservation, we need a lemma that sort of says something like this, where E is well typed and K is well typed with respect to the translation of E, and then translating E with K should be well typed, right? So how do we encode more invariance? We just add more types. So in particular, we encode target contexts as a dependent types consisting of 3 parts. The first is the term that's expected to go into the hole in the target context. The second is the type of the term that's expected. And the final one is the type of the entire full program. So now given this type, we can restate our key lemma as follows, where intuitively what we're saying here is the source expression is well typed, the target context is well typed with respect to it, so putting them together should give us a well typed target program. So now that we have this key lemma, I can prove type preservation for you in 3 easy steps. So we have our top level theorem here as before. Here we have that the translation of E is defined with the empty context. And we can type the empty context as following. It's expecting the final translation of E at its translated type. And since the empty context doesn't really have anything surrounding it, well, we get the translation of A type back. And then using our new lemma, we know that our translation has the translated type, and we're done. So all that's left is proving the key lemma, and it's a bunch of smart people here, so I was hoping to get a lot of help here. I'm just kidding. So this follows by induction on the source program E and context typing in particular, because we're building up a lot of the program now in our target context, so we need to show that that is well typed. I mentioned very early on extensional equality. So how does this relate back to what we're doing here? Well, in particular, in the key case of our lemma, when translating dependent if expressions, we find that we need extensional equality. So let's talk about that. So here I've put it back up on the screen so we can kind of remember what's going on here. And we find that when we're trying to prove the case for dependent if expressions, that the target context we build up is not well typed. And this is very similar to why our refactor wasn't well typed originally. So in particular, the target context is expecting the term, which is the translation of the entire if expression, but then we translate it with the branches. So really now it needs to expect the translation of each branch. And if we think back to our proofs of equality, how we change, the terms here in our types, we really need some way of changing the term inside of the type of K. So we need some kind of subs term, right? But unfortunately, we can't actually determine at what point will the target context be plugged with the final value of each branch. So we're kind of stuck trying to determine where to insert these casts, essentially. In particular, even if we did find out where to insert these casts, we might end up with something that's not in ANF. So the way that we achieve this is we actually just have this assumption that in the first case, that the condition is true. And so we reflect it to the type system using extensional equality, and then the proof works out quite simply from there. So I'd like to talk a little bit about the benefits of this approach, because extensional equality has some known problems, but we talk about that a lot in our paper. In particular, we get a very standard ANF translation in our paper, one that you would probably find for most models of functional languages. And we don't end up generating very large target terms just to show that they're well typed, which is a great benefit for compilation. Don't want really big programs. And then we find in our paper that this approach is very easily adaptable for the join point optimization and other branching expressions like match. So to conclude, our intermediate type systems need some way of encoding extra information in them. In this case, we did this by adding these proofs, but we also need to use this extra information somehow. So we did this using extensional equality, and we found that in our translation, we needed a little bit more extra information about everything that was going on, so that we included target context typing as well. Thank you, and I'm very excited for lunch.